Chapter 16 is about random variables. I will give you a definition of what that means in a second. But you need to keep in mind that it's still just probability. That's all it is. We're moving away from the probability things that you've done in the past. So we're moving away from, here's this probability of this happening, and multiply them together. We're moving away from that. We're going to get more into real-world scenarios where, okay, you have this instance. There are 3 possible outcomes, and you're trying to make decisions based on those outcomes. A lot of the examples in this chapter are gambling related. As in, you could play this game, and here are the possible outcomes and the possible payouts. Would you play or not? And you need to base that on some sort of mathematics. Okay? So it's not really necessarily that hard. I'm going to tell you to do it. It's going to be fine. But generally, you're moving away from what you've seen before, if that makes sense. All right. In this chapter, this is what you need to know, because I didn't put it all up there, because you know how our book uses an example, and then you have to know the example to know what they're talking about. They're talking about actuaries, and actuaries assess risk for insurance companies, and they're the ones that set all the rates and decide how much to charge you to make sure that the insurance company doesn't lose money. Okay? So their job is to assess risk. So in this scenario, they're saying you have bought an insurance policy, and you pay $50, it's like a month or a year or something. I think it's a year, $50 a year for the insurance policy. That's not bad. If you die, then it pays out $10,000. If you're disabled, it pays out $5,000. Of course, if neither happens, you just keep paying for it each year. That's how insurance works, right? So they're just talking about, well, how do insurance companies then not lose money if they're only charging you $50, right? But then they're going to pay out $10,000 anyone that passes away. It seems like it doesn't make sense. The numbers don't seem to add up just initially. So we're going to talk about some things here with probabilities and what we would expect to happen to see if really they're undercharging you or not. So we're talking about insurance, okay? All right, so we're going to talk about the insurance company, and I've got a lot of vocabulary to throw at you. All right? We're trying to figure out the amount the company pays out on an individual policy. So if there's 10 of you sitting in here and you all have the same insurance policy, they're talking about paying out to each of you. Okay? Now this event is called a random variable because its numeric value is based on the outcome of a random event. Being disabled and passing away are generally random events. Okay? We can't predict generally when we're going to pass away, that kind of thing. When we have random variables, we use capital letters. This is going to be really important. I'll go through all this notation when we're doing an example, but the notation will be important. So we use capital letters like X to denote a random variable. There's a box in your book. It says generally we have X, Y, and Z, but it could be any letter you want it to be. But a random variable is defined with a capital. A random variable is defining the entire event, what you're really talking about. So in this case, we're talking about payouts to individuals from the insurance company. Okay? Now, each one of these big events has different outcomes. We already talked about it. You could pass away and get paid out $10,000. You could be disabled and get $5,000, or nothing happens to you and you get nothing. Right? Those are the 3 outcomes. Each one of those individual outcomes is denoted with a lowercase letter. Right? So in this case, capital X is the amount that they're paying out to the individual policy. Lowercase x is each one of the individual outcomes of this broader event. Okay? Because we can list all the outcomes, right? $10,000, $5,000, nothing. Because we can list all the outcomes, we're going to call this a discrete random variable because I know everything that could happen. There's no maybe you get $8,000 for something else. Like these are the 3 possibilities. If we didn't know all of the outcomes, That'd be a continuous random variable, and we'll talk about those later in the chapter. So for right now, we're just talking about discrete random variables. The collection of all the possible values and the probabilities that they occur is called the probability model for the random variable. We have lots of models in statistics. So for example, think back to chapter 7, 8, 9, 10. We were doing scatter plots and linear equations to predict things, right? Y-hat equations, remember those? Well, we had to make a model there, but in that case, a linear model was just an equation. In this case, a probability model is going to just lay everything out for you in a table. That's all it is. So that you can see it all, see the outcomes and the probabilities next to each other. It's generally just a list to make sure you're keeping track of everything that's happening. And then from that probability model, we can answer questions. Okay? So for example, it says the death rate in any year is 1 out of every 1,000 people. And that another 2 out of 1,000 people suffer some kind of disability. Those are the probabilities of these events occurring. Then we can display the probability model for the insurance policy in a table like this. So again, capital X is going to be the amount of payout to each individual we have 3 different outcomes with their respective payouts and their respective probabilities. That's the probability model, is this table. That's all it is. Okay? Does that make sense? All right, so we're going to practice real fast. We're going to go back and forth today. We're going to practice by making our own for a different scenario to make sure you know how to make the model. Okay? It says you draw a card from a deck. If you get a red card, you win nothing. If you get a spade, you win $5. For any club, you win $10, plus an extra $20 for the ace of clubs. Okay? And it says in part A to create a probability model for the amount you win. So we're going to do that. First thing we need to do is we need to define our random variable. And you're not going to think this is very important, but notation-wise it is. Again, the random variable is the big idea. What are we actually looking for in this question? We're looking for the amount you win. We're doing a probability model for the amount you win. That's the overarching thing. How much are you going to win playing this game? So we'll define that as X. That's what we're trying to figure out. We're trying to look at the probabilities of how much you're going to win. And you'll see where this all comes together in a second. So we have some different outcomes. Each of those outcomes has a payout of some monetary amount. Your outcomes in this case are what card you draw. And then associated with that is some probability. The probability that you win whatever. This is the notation that you're going to see a lot right here. That means the capital X is the amount you win. And the little x is an individual outcome. So remember when you draw a red card, you win nothing? So the associated probability is going to be the probability that the amount you win is nothing. That's just what that notation means. So we're going to list our outcomes here. So the first one is you get a red card. I'll read through the question. So it says, if you get a red card, you win nothing. So the amount won is $0. Then what's the probability that you get a red card from the deck? 50%, 1/2. There's 26 red cards, right? Out of 52. Doesn't matter. Decimal fraction form, whichever works. For what you're going to do later, you might want to have a decimal form. Everyone got that? Okay. So then the next one says if you get a spade, you win $5. So that's my next outcome. How many spades are there? 13, which that ends up being a fourth, right? Now the next sentence, it says, for any club, you win $10 plus an extra $20 for the ace of clubs. So that's technically two separate outcomes, right? We want to split that up accordingly. So the first one's going to be a club that's not the ace, because that one's more specific. So if you get a club that's not the ace, how much are you winning? $10. And how many clubs are there that aren't the ace? 12 out of 52, which ends up being approximately 0.231. Okay? Ish. And then the last one was the ace of clubs. If you got the ace of clubs, it said you got an additional $20, so 30. And how many ace of clubs are there? Which again is approximately 0.019. Okay. Now if you look at the fractions, since I rounded, the decimals won't work out as pretty. If you look at the fractions, what do all the fractions add up to be? 52 out of 52, right? In a probability model, you still have to have probabilities that add up to 1. If they don't, you're missing an outcome somewhere. Okay? But this is our model. This is part A. This is what they asked us to do. Okay? Now, this is why these are important. So back with the insurance question and this one. The whole point is I want to know, I don't know what's going to happen. I want to know what might happen, could happen. I want to know what I should expect to happen. All right? So with the insurance question, the insurance company, actuaries, you're looking at, you're paying $50. How much are they really paying out to you? They're probably going to look at that on average, right? So they can see individual people. For this question, part C is going to say, what would you be willing to pay to play this game? Well, then I would want to know on average how much I was going to win, right? That would probably be helpful in assessing the risk of playing this game or assessing the risk of charging $50 for an insurance policy. All right? So how do I find averages when there's different probabilities and different things happening? How am I going to figure out what I expect to happen? So we're going to do this. We want to find an average. In this case, it's not based on sample data. This is all theoretical, right? We don't really know what's going to happen. This is theoretical probabilities. They're saying that 1 out of 1,000 people dies each year. That doesn't mean it's going to happen every year, right? This is not a sample data. So we are not doing X bar when we have sample information. This is like theoretical, hopefully this is going to happen type stuff. So we're using mu about the population, not about a sample. Okay, does that make sense? In this case, we're trying to figure out what expects to happen. So when we're talking about probabilities, the mean is called the expected value. If it asks for you to find the expected value from a probability model, you're finding the mean. When you have different probabilities or different values for different outcomes, when you're finding an average, you have to do a weighted average. Do you all know what a weighted average is? So that's what they're going to do. Here's an example with the insurance question. If you go back to the model, if I find a weighted average, I'm going to take each payout and multiply by its probability and then add it all together, right? Well, so that's what we're doing. So it shows me here that the expected value with this insurance risk situation is $20. Remember, X was individual payout. So you're paying $50, and on average, they're going to pay out to you $20. So how much profit are they making in each person? $30, right? Can you actually get $20 from the insurance company each year? No. You're going to get $10,000, $5,000, or nothing. But on average, they're only paying out to you $20. So they're making a profit. That's why they can get away with only charging you $50. Does that make sense? It would be helpful to know those things, right? Back with the card situation, again, C is going to say, what would you be willing to pay to play this game? If it's free, I'm playing all day, I don't lose anything, right? I'm making money. Well, they're going to make you pay to play the game like they do everywhere else. So it would be nice to know what you would expect to win. That's not guaranteed, but you aren't going to pay more than what you would expect to win, right? So we're going to find the expected value. So again, the expected value is just the mean, and you're just taking all of the outcomes and multiplying by their probabilities and adding it all together. So that would be 0 times 1/2 plus 5 times 0.25 plus 10 times 0.231 plus 30 times 0.019. The expected value ends up being $4.14-ish. Was $4 an option? Are you actually going to win $4.14 at any point? No. But on average, you would win $4.14. So how much would you be willing to pay to play this game? Definitely not more than $4, right? Now, if the options are 0, 5, 10, and 30, depending on how risky of a person you are, maybe you're only going to pay 50 cents to play. Maybe you're going to pay $4 to play. That's totally personal opinion. That's based on your personal risk assessment of your money, right? But again, it's nice to know how much I expect to win before I just start doling out cash. Right. But they're asking how much you would pay to play. They're not setting the price for the people that are doing the game. That's a good thing. If they ask the other way, that's a good thing to think about. Okay? If Ian's talking about if you were the one setting up the game, you want to make a profit. So you want to make sure you charge more than you would expect them to win. So you're making a profit. So think about how they're asking that question to you. So the expected value was part B of this question, and then C was how much you would pay. Again, that's personal opinion. So if you're checking your answers for a homework question against mine, my personal opinion for part C may be way different than your personal opinion for part C. Okay? Does this make sense, though? We're doing a probability model so we can assess risk of some type. All right? And so we can see kind of what we're expected to win or expected to pay or something like that, so we can go about our business. So we're going to play a game. Okay? We'll come back to this in a little bit.